Hi guys, I am back for another video. I apologize for my casual appearance, but it's our mini spring break, so it's Easter Sunday, and so I'm kind of doing a little casual thing. It's almost like a behind-the-scenes tour, except there's no tours, and we're not going behind the scenes. But I'm casual. So, okay, we have to talk about titration curves today. Titration curves are when we take, generally we're talking about when we take an acid and a base and we titrate them together, or we mix them together in very specific amounts and see what happens to the pH. So for example, we might take a beaker of acid and we might add a base very slowly and carefully with those titration burettes. They're those big tall burettes with the little stopcock in the bottom where you're counting the drops and you all hate it and you're never very accurate. But anyway, we could take a look at the pHs, and that's what we're going to do today. We're going to take a look at how the titration curve changes based off of if it's a strong acid and base, or if it's a strong acid with a weak base, or a weak acid with a strong base. You're going to love it. Okay, so let's start with the simplest one. Let's talk about strong acid and strong bases. Strong acid and a strong base. Okay, what we're going to do is we're going to take snapshots of what species or what chemicals are present throughout the experiment, and then we'll graph what the pH should look like as time goes on. Okay, well, let's say we start with a beaker of acid. So we start with a beaker of acid, and we're going to drip base into it. So let me put a little drawing up here. This is a beaker. That's the acid. I'm just going to label it A. It's going to spell it acid, but it's not going to work. So let's just label it A. Then I have this titration burette. It's a very long, thin burette with a little point at the bottom. And we're dripping in. That's base. Now I'm going to spell it base because I have a lot more room. Okay, these are strong, so we could say HCl and NaOH, or you could let your imagination go wild and choose any monoprotic acid with a strong base. But I'm going to do HCl and NaOH. Okay. So, at the start, in that beaker, there are two things. There are two things present. There is, first off, H2O, right, because there's water. Yes, this is all the water. And there's HCl. Kind of. These two things never really exist together in nature, right? HCl is a strong acid, so as soon as I put it in water, it dissociates. So I really don't have H2O and HCl. I really have H2O and a dissociated strong acid, which would be a hydronium and a chlorine. Okay, so that's really what's present. I have my water, tons of water, just absolute massive amounts of water, and some hydronium and some chlorine. Okay, we have a lot more water than we do acid. Okay. Now, at the midpoint, and I'll tell you what the midpoint means in a second, but at the midpoint, we are going to have our water, because we will always have water. We're going to have some HCl, which we know is a lie. It's really hydronium and chlorine. Right? And we've started adding some base, right? We've started adding some base in here. So we're going to have some Na pluses, because I'm going to say it's NaCl. Okay? Or I'm sorry, NaOH. So my base is NaOH. Oh, that's horrible. NaOH. And my acid is HCl. Okay, those are just our examples. So I would have a little Na+. You might be going, well, Mr. Wood, OH, where'd the OH go? I'll be like, students, the OH reacted with my hydronium to produce even more water. Right? When I have NaOH and HCl react, when I have my overall reaction, let me draw it over here. When I have NaOH plus HCl react, it's going to form H2O and NaCl, right? The H2O, adding more in there. The NaCl, right there, and right there. Okay? So that's kind of halfway to the equivalence point, or the midpoint of my titration. So you can think of it as I'm halfway there to them being equal. Now the equivalence point, let me add a little bullets here. Okay, the equivalence point is when my acid and base in the beaker are equal. That's why it's called the equivalence point, when they're equal. So when I've added enough base that the amount of HCl and NaOH in the beaker are equal. We would expect the pH at this point to be 7. Okay, so at the equivalence point, I'm going to have H2O, I'm going to have tons of water. I'm not going to have any HCl anymore because all of the HCl should have reacted with NaOH. So instead, I'm going to have my salts that are left over. I'm going to have Na, and I'm going to have Cl. Okay? All of the OH and all of the H's have reacted together. It is perfectly neutral at this point. I just have water and essentially salt. Okay. Now let's say we keep going. Let's say we go past our equivalence point because, hey, why not? It's chemistry, and chemistry's fun. So let's say I go past my equivalence point, and I'm going to abbreviate equivalence point EQPT. That's fun abbreviations. All right. Well, past my equivalence point, I'm still going to have my water. I'm still going to have the Cl in there because that didn't go away. I'm still going to have the Na in there. But I'm adding extra NaOH. Right? I'm adding extra NaOH. This is past where they're equal. So I'm keep dripping that NaOH in there. And, well, so I'm going to have some OH. Right? If I keep adding NaOH into my beaker after all the acid's used up, I'm going to still have OH. Okay. Now, let's say we were to graph this. Okay, let's say we were to graph this. And we're going to call it pH on the side. And we will say volume added. How about that? Alright, so this is as I add base and the pH. Well, before I add any base, my pH is going to be low because it's acidic and acids are low. And as I add my base, my titration curve is actually going to look like this. There's a very, very sharp point in the middle. At the very center of that sharp point, that's my equivalence point. Right there. Okay? That was supposed to be an arrow. It didn't work out very well. I don't know why I felt the need to draw an arrow when the word was right next to the point, but I did. So, as I'm titrating, as I'm adding base, my pH goes up. And you'll notice you're going to hit a point where my pH changes drastically. That's because my acid and base are in equilibrium. They are equal amounts. So any little bit I add shoots that pH up. And then after I get there, after I kind of get up here, I'm adding more base, but it's not really changing my pH much because there's so much OH in there. So this is my equivalence point. This is when they're equal. And the halfway to equivalence point is right about here, or the midpoint. I'm not going to draw an arrow. That didn't work well. That's the midpoint. I'm halfway to my equivalence point. Okay, so I'm halfway to my equivalence point. So if my equivalence point, let's drop a line, was right here, my midpoint should be halfway. Right? Not perfectly halfway, but we'll call it perfect. Okay? So my midpoint is when I've added, when I'm halfway to my equivalence point. And that midpoint is going to become really important when we talk about weak acids and weak bases. Okay, so that's strong and strong. Nice and simple, kind of makes sense. Alright? If you didn't quite follow at the beginning, you might want to rewind it and watch the first part again, because it's not tricky, but if you weren't really knowing what we were going for, it can be. Okay, so we are going to go, we're going to add a weak base now. That's going to be fun. A weak base, so I'm going to use ammonium. Because I can. And all the other weak bases are kind of complex, and I can't remember their formulas. Okay, so this is a strong acid and a weak base. So a strong acid and a weak base. Okay, so I have a titration curve. I'm just going to plot my titration curve. It's going to look the same. Let me try and make a better halfway to equivalence point. There's a better one. Alright. There's my titration curve. There's my equivalence point. There's my midpoint. Just so you can reference the graph while we're going through this. Okay, so when I start, it's going to be the same thing as before. I haven't added any base, so I'm going to have water. And I'm going to have my HCl, which we all know is now a vicious lie because it's really hydronium and chlorine. Right? Okay, so that's what I start with. At my midpoint, or it's sometimes called the halfway to equivalence point. At my midpoint, I still have my water. Right? I still have acid, right? I still have my acid. I still have my HCl, which we know is a lie. There we go. But I also have some of the reacted base, right? I probably should have drawn the equation over here, but let me do that. It's NH3 plus HCl is going to form NH4 plus HCl minus, right? Donates the proton, accepts the proton, turns into that. So, at my midpoint, I'm going to have some NH4 plus. Alright? I'm going to have some NH4 plus present. Okay. Also at my midpoint, let's remember there's another kind of reaction going on here, right? Remember that NH4 plus will dissociate, right? It will dissociate to form NH3. Okay, it will dissociate to form some NH3. So I am going to have some, probably NH3 here. But be aware, as soon as this forms, it's going to react and turn back into NH4. So at this point, I'm going to have almost no NH3 present. So I hesitate to put that, but I put it here so it doesn't confuse you at the equivalence point. But be aware that you really don't have this present because it's going to react with your hydronium right away, and it doesn't really, this really isn't a true kind of equilibrium-ish. But just bear with me. This will make sense in a second. It's here, but it's not really there in any significant detail. At my equivalence point, I'm going to have my water that I started with. Now, I have all my acid and all of my base have reacted together. So I don't have any HCl. I don't have any hydronium. I have chlorine. I have NH4 plus. Alright? And here's where that dissociation is important. I have some NH3. Okay? I have some NH3 because this will dissociate in water. And since there's no acid to immediately react with it, this dissociation is free to take place. I hesitated putting it up here because this is immediately going to react with the hydroniums present and turn back into NH4. This really doesn't exist. But here, the hydronium's gone. So now it can exist. Alright, so I put it up here so you're aware that it happens, but it's not really in any appreciable amount. You really couldn't ever find this in solution here, but you will find it in solution here. And that's going to do something very, 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 very important. That's going to do something very, 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 very important. This right here, in this dissociation, from my NH4 to my NH3, in this dissociation, this has to donate a proton. This is a conjugate acid of this base, right? This is the conjugate acid. NH4 is the conjugate acid of ammonium. Therefore, the equivalence point will be slightly acidic. Or less than 7. So in this pH curve, in the other one I didn't draw it because it was assumed that it was neutral. In this pH curve, 7 is probably right around here-ish. Notice my equivalence point falls short of 7. It is, even though my acid and base have been added in equal amounts, the solution is acidic because I have a conjugate acid. I have a conjugate acid. And when it dissociates, it produces a hydronium. It produces that hydronium, and it's in very small amounts, and it makes it acidic. Okay? Now, after my equivalence point, after my equivalence point, I still have the water that I started with. I still have the Cl minus. I still have the NH4 plus. And I have more NH3 because remember I'm adding a base, so it's dripping in there, and the basicness shoots up. My pH shoots up. Okay. The important takeaway here in all of this is right here, that at my equivalence point, because I have a conjugate acid present, my solution will be slightly acidic. Okay. Now, let's do this again, only let's do this with a strong base and a weak acid. I should have kept that titration curve. I always think I should keep this titration curve. And then I never do. Okay, so my base, we're going strong base. So I'm going to go NaOH again. And we're doing weak acid. So I'm going to say acetic acid. Alright, acetic acid, just to kind of mix it up. Hydrofluoric acid is always a big one I use. Cyanidic acid, hydrocyanidic acid. So we'll do acetic acid. It'll be fun. You'll love it. Okay, so it's a strong base. Weak acid. Alright, so I'm going to start. Oh, let me draw my titration curve. pH. Okay. I just put a V for volume. You get the point. I was sitting there for that a little while. Okay, so I have my equivalence point, I have my midpoint. Once again, let me move my midpoint over a little bit so it's a little bit more. It's halfway to the equivalence point volume-wise, so yeah. Kind of. Close. We'll call it close enough. Okay, so when I start, all I have in my beaker is acid. So I have CH3, COOH. I have some water. Probably should have listed water first, because I have been constantly. And then you'll notice I also have some CH3, COO minus, and hydronium. Okay? Now, I have all of these present, right? Because this is a weak acid, so this will not dissociate fully. So I'm going to still have some of this present, but most of it will have dissociated. Excuse me. So most of it will have dissociated. So let's start adding some base in there. So I start adding some base. I'm going to have CH3, COOH. I'm going to still have some acid. Right? It's still going to be acid present because I haven't added all the base. I still have my water. Once again, should have listed that first, so it's kind of out of the way, but I didn't. I'm going to have some Na+, right, reacted. I should draw the reaction. I will in a second. All right. I'm going to have some conjugate base. And I'm going to still have my hydronium. Okay. Now let me write this reaction down so we kind of know what we're working with here. Na plus CH3 COO minus plus H2O. Kind of write out a little bit of room. Okay, so that's kind of what's going to produce Sodium acetate would be NaCH3COO, so if we dissolved all the water and those combined together. I kept them apart just for simplicity's sake because they're kind of big, long, and a little bit complicated. So these are all the species I have present. At my equivalence point, alright, all of my acid will have reacted with all of my base. So all I'm going to have present is my water. Let me get that out of the way first. My water. I'm going to have some Na plus, and I'm going to have CH3COO minus. Alright? Now, here's the deal. Here's the deal. Along with this, it's going to accept protons. This is the conjugate base of acetic acid. So it's a base. So I am going to have a dissociation here, or I'm going to have a reaction here with water. Right? I'm going to have a reaction and it's going to produce this. Right? I'm going to have an equilibrium between my conjugate base and water, the water present. So I'm going to have a reaction between these two. And it's going to produce some of this. Okay, so it's going to produce some of this. When this reacts with water, it will produce some of this. That's important because it's slightly basic. Probably saw that coming. Or above 7. So when I put my pH here, I'll put 7 right here. So my equivalence point is actually going to be slightly above 7. Now, I kind of made that drastically above 7, but who am I kidding? That graph's kind of a little bit messed up because of my midpoints everywhere. Okay? And then past my equivalence point, this is where I'm going to get pretty much my H2O. I'm going to have a lot of Na. I'm going to have a lot of OH. I'm going to have a whole lot of CH3COO minus. I will have maybe some acetic acid forming, but it's going to react with the OH immediately, kind of in our past example where that happened, except that happened here. So down here, that's going to dissociate with the water. It's going to immediately react with the OH present and turn back into that. So kind of is present, but not really in any appreciable amounts. Okay, so that pretty much sums up the video. I want to just draw the graphs very, very quickly for you, just so you're aware of what's going on. Remember, we drew all these graphs starting acidic and turning basic, but we could just as easily go the other way. We could have a base in here and titrate with an acid. So the titration curves could go both ways. It doesn't really have to be one way or the other. Traditionally, they're just written this way, and so you just get in the habit of doing that. But it doesn't have to be that way at all. Okay, so just to recap. Let's say I've got a strong. Titration curve is going to look like this. My equivalence point is going to be exactly at 7. Alright, so when all the acid and the base react, it's going to be at 7. Let's say I've got a strong acid, weak base. I'm going to just start abbreviating because I don't want to take any more of your time than I have to. When I do this out, my equivalence point is going to be right here. It's going to be below 7. Okay, it's going to be below 7. When I have a weak acid, why didn't I abbreviate? I don't know. A strong base, once again, didn't abbreviate. What's going on with me? When I have a weak acid and a strong base, here's my equivalence point. It's going to be above 7. So 7 is going to be down here. It's going to be above 7. Okay? And then, last but not least, we really didn't cover this very much, but when I have a weak and weak, the equivalence point will depend on the strength of the different acids, the Ka and the Kbs of the different acids. But generally, the important thing is to note that my titration curve is not nearly as steep. Excuse me. I have this big, nice, steep titration curve. On a weak one, it's a little bit punier, just because of the buffering effects of the strong and weak acids. Okay, so that covers our titration curves. We will talk about the importance of the midpoint, as well as a couple of different things later on in some later videos. Hope you enjoyed. Thank you, and good luck.